Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the deepest mysteries of cosmic time itself. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The universe whispers its age through light that has traveled longer than memory can hold. 13.8 billion years, the textbooks say with quiet confidence, marking time from that first brilliant expansion we call the Big Bang. Yet in the darkness between stars, in the subtle mathematics of cosmic microwave background radiation, something older stirs. The afterglow of creation itself carries patterns that seem impossibly mature, like finding ancient oak trees in a garden that was planted yesterday. This faint radiation bathes everything, every grain of sand, every sleeping bird, every distant galaxy spinning in its appointed dance. At 7 degrees above absolute zero. It represents the cooled remnant of that moment when the universe first became transparent to light. Roughly 380,000 years after the initial expansion, the temperature hovers just barely above the absolute stillness of space, warmer than the void by less than the difference between ice and slightly cool water. Scientists map this background with extraordinary precision, measuring temperature variations across the sky that amount to mere millionths of a degree. These tiny fluctuations reveal the seeds from which all cosmic structure would eventually grow. But here dwells the quiet mystery that keeps cosmologists awake in observatory control rooms scattered across mountaintops and frozen Antarctic plains. The patterns in this ancient light suggest a universe that had already achieved remarkable sophistication by the time photons first began their free journey through space. The temperature variations show correlations across vast distances, regions of space that should never have had time to influence each other according to standard models of cosmic expansion. It's as if the universe began its growth with blueprints already drawn, architectural plans that required eons to develop in some prior workshop of space and time. The cosmic microwave background radiation tells 3 stories simultaneously, each layer revealing deeper mysteries. First, it confirms the Big Bang theory with elegant precision, showing exactly the thermal signature predicted for a universe that began in a hot, dense state and has been cooling ever since. The spectrum matches theoretical predictions with accuracy that would make a clockmaker envious. Second, it reveals the tiny density variations that would eventually collapse under their own gravity to form the first stars and galaxies, compressions and rarefactions in the primordial plasma like wrinkles in cosmic silk. Third, and most mysteriously, it displays a level of organization that seems to require more time than the universe has supposedly existed. The cosmic microwave background fills every cubic centimeter of space with roughly 400 ancient photons, invisible to human eyes but detectable by sensitive instruments that can measure temperatures to millionths of a degree. These photons have been traveling freely since the moment electrons first combined with nuclei to form neutral atoms, ending the epoch when the universe was opaque to light. Before this moment of recombination, photons scattered constantly off free electrons in a cosmic fog so dense that light could travel no farther than a modern city block before colliding with matter. Only took 13 billion years to forget where the blueprints came from. Only required the patience of empty space to preserve every photon from that ancient moment. Only needed the entire observable universe to serve as a cosmic photograph, frozen in microwave frequencies and stretched by expansion until radio telescopes can detect its whisper, like a planetary exhale that lasted billions of years. This background radiation continues to cool and redshift as space itself expands. Originally, these photons blazed with the temperature of stellar surfaces, roughly 3,000 degrees Kelvin, hot enough to melt copper, but the expansion of space has stretched their wavelengths, cooling them to their current frigid temperature, barely warmer than the absolute zero where all atomic motion ceases. Every second, the universe grows larger, and these ancient photons grow slightly colder, their energy diluted across ever-increasing volumes of space. The mathematics grow quiet around this paradox of cosmic organization. Computer simulations that attempt to recreate the early universe struggle to produce the observed patterns within the standard timeline. The correlations seen in the cosmic microwave background require processes that operate over scales larger than light could have traveled in the supposed age of the universe at that time. It's as if different regions of the early cosmos had time for lengthy conversations about how to coordinate their temperatures before the expansion began in earnest. Modern satellite observatories detect polarization patterns in this ancient light, swirls and eddies that suggest magnetic fields and plasma physics operating on cosmic scales when the universe was still a glowing fog of hydrogen and helium. These polarization signals add another layer to the mystery, revealing organizational structures that emerge from gravitational and electromagnetic processes requiring extensive time to develop. The patterns show handedness, a cosmic chirality that implies the early universe possessed a sense of direction and flow. Temperature maps of the cosmic microwave background show what researchers call acoustic peaks, harmonic overtones in the early universe's expansion, like sound waves frozen in light and preserved across cosmic time. These peaks occur at specific angular scales across the sky. Corresponding to the maximum distance, acoustic waves could have traveled through the primordial plasma before the universe became transparent. Yet the sharpness and clarity of these peaks suggest a universe that had already undergone many cycles of compression and rarefaction, like an instrument tuned by invisible hands. The acoustic waves themselves represent pressure oscillations in the photon-baryon plasma, compression waves racing through the early universe at roughly one-third the speed of light. When electrons and protons combine to form neutral hydrogen atoms, these waves froze in place like ripples on a suddenly solidified pond. The wavelengths of these frozen acoustic oscillations determine the size scale of galaxy clusters and cosmic voids that form billions of years later. Perhaps the universe began its current expansion from a state that was already ancient. Perhaps what we call the Big Bang was simply the moment when an eternal cosmos decided to become observable, emerging from some deeper phase of existence like a whale surfacing from oceanic depths. The whisper of ancient light carries these possibilities across 13 billion years of emptiness, patient as stone, persistent as gravity itself. Measurements reveal subtle asymmetries in the cosmic microwave background, tiny temperature differences between opposite hemispheres of the sky that hint at motion or structure on scales larger than the observable universe. These asymmetries challenge the fundamental assumption that the universe looks the same in all directions when viewed from any location. They suggest that our observable cosmos may be embedded within something larger and older, like a small clearing within an infinite forest. The cosmic microwave background radiation continues its quiet testimony, cooling by imperceptible degrees as the universe expands into tomorrow and tomorrow. In its patterns lie the memories of a time before time, when space itself was learning the rules it would follow for eternity. Every microwave photon carries information from an epoch when the entire visible universe could fit within the orbit of Neptune, yet somehow already contained the seeds of every galaxy that would ever shine. In the spaces between galaxies, where starlight fades to whispers and matter spreads thin as forgotten breath. An invisible architecture holds everything together. Dark matter weaves through the cosmos like cosmic scaffolding, 5 times more abundant than the atoms that make stars and planets, and the quiet thoughts of astronomers peering into telescopes on cold mountain nights. Yet this hidden mass reveals itself only through its gravitational embrace, bending space and shepherding ordinary matter into the patterns we observe today. Computer simulations attempt to recreate the universe's evolution, beginning with tiny fluctuations in dark matter density and watching them grow under their own gravity across cosmic time. These digital universes bloom into vast networks of filaments and nodes, dark matter halos that will eventually cradle galaxies like cups holding starlight. But the simulations require something the standard timeline cannot provide: more time than the universe has supposedly existed to build the massive structures astronomers observe in deep space surveys. The largest galaxy clusters span tens of millions of light-years. Gravitational cities containing thousands of individual galaxies bound together by dark matter scaffolding that outweighs all visible matter by factors that would make accountants weep. These clusters show evidence of multiple merger events, cosmic collisions that require hundreds of millions of years to complete even after the initial gravitational encounter. The mathematics of cluster formation demand a universe with more patience than current models allow. Dark matter particles, whatever they may be, interact only through gravity and possibly the weak nuclear force. They pass through ordinary matter like cosmic ghosts, millions streaming through every human body each second without disturbing a single atom. Yet collectively, their gravity shapes the largest structures in the universe, creating a cosmic web of filaments and voids that stretches across billions of light-years. This web shows organizational complexity that suggests extensive evolutionary time. The mystery deepens when simulations attempt to match observed galaxy rotation curves, the speed at which stars orbit their galactic centers. Visible matter alone cannot account for these rotation speeds. Stars in the outer regions of galaxies move too fast to remain bound by the gravity of observable matter. Dark matter provides the additional gravitational anchor, but its distribution must be precisely tuned to match observations. This tuning implies a long period of gravitational evolution and interaction. Only took 5 billion years longer than we thought to get the cosmic web properly strung. Only required dark matter to outnumber ordinary atoms by 5 to 1 without leaving any direct calling cards. Only needed the entire observable universe to serve as construction site for an architecture built from invisible materials, like a cosmic circulatory system. Dark matter filaments channel ordinary matter along their gravitational highways, directing the flow of gas and dust toward the intersections where galaxies form. The largest of these filaments stretch across hundreds of millions of light-years, requiring light travel times that approach the supposed age of the universe just to span their length. Their gravitational influence must have been establishing itself long before the cosmic microwave background became transparent. Gravitational lensing reveals dark matter's presence through the subtle distortion of background galaxies, their images stretched and magnified by intervening dark matter halos like light passing through cosmic magnifying glasses. These lensing maps show dark matter concentrations that sometimes appear disconnected from visible galaxies, as if the invisible scaffolding preceded the construction of luminous matter. The degree of gravitational focusing observed requires massive structures that take considerable time to assemble. The cosmic web of dark matter shows hierarchical structure, smaller halos merging to form larger ones in a process that cosmologists call bottom-up structure formation. Yet observations reveal massive galaxy clusters at such high redshifts, corresponding to such early times, that the hierarchical assembly process seems accelerated beyond what dark matter physics should allow. It's as if the universe began with a head start on structure formation. Dwarf galaxies orbiting the Milky Way show orbital patterns that suggest they've been gravitationally bound to our galaxy for many billions of years. requiring stable dark matter halos that predate the formation of the galaxies themselves. These satellite galaxies follow predictable paths around their parent, like planets orbiting a star, but their orbital periods span hundreds of millions of years. The stability of these orbits implies gravitational systems that have had extensive time to reach equilibrium. Perhaps dark matter began clustering long before the epoch we associate with the Big Bang, creating gravitational wells that would later capture ordinary matter when it finally decoupled from radiation. Perhaps the invisible architecture of the cosmos has been under construction for far longer than the visible universe suggests, building foundations in a prior phase of cosmic evolution that left no direct trace except in the patterns of matter distribution we observe today. The cosmic microwave background itself bears the imprint of dark matter fluctuations, temperature variations that correspond to regions where dark matter was beginning to clump when the universe first became transparent. But these fluctuations show amplitude and correlation that suggest the dark matter had already been evolving for considerable time before photons began their free journey through space. Modern surveys map the three-dimensional distribution of galaxies across billions of light-years, revealing the cosmic web in unprecedented detail. The resulting maps show galaxy filaments, walls, and voids arranged in patterns that require gravitational evolution over timescales longer than standard cosmology permits. The voids themselves, vast regions nearly empty of galaxies, represent gravitational watersheds where matter has drained away into surrounding filaments, a process that operates slowly even by cosmic standards. Dark matter's patient construction project continues today, invisible hands guiding the slow dance of galaxy formation and evolution. In computer simulations, dark matter halos grow through accretion and merger, gradually building the massive structures that will host the largest galaxies. But matching observed galaxy masses and distributions requires fine-tuning the initial conditions to a degree that suggests the process began much earlier than current models assume. The scaffolding holds everything together with gravitational threads stronger than steel, yet more delicate than spider silk, supporting the weight of galaxies while remaining forever hidden from direct observation. Only through its influence on visible matter does dark matter reveal its presence, like detecting wind by watching leaves dance in an otherwise still forest. The oldest stars burn with a light that carries secrets from the universe's youth, yet their spectra whisper of impossibilities that challenge everything astronomers thought they understood about cosmic time. These ancient suns, formed when the universe was supposedly young and simple, contain traces of heavy elements that should not exist according to standard models of stellar nucleosynthesis and cosmic chemical evolution. Iron, silicon, magnesium, and other metals flow through their outer atmospheres like cosmic memories of stellar deaths that supposedly never had time to occur. Population 3 stars, the theoretical first generation of suns born from primordial hydrogen and helium, should burn pure and metal-free in a universe that had not yet forged elements heavier than lithium in stellar cores. These hypothetical giants would have lived fast and died young, exploding as supernovae to seed the cosmos with the first heavy elements. Yet astronomers have never definitively observed a truly metal-free star. Despite decades of searching with instruments sensitive enough to detect metallicities 1,000,000 times smaller than the Sun's composition, even the most metal-poor stars discovered in the Milky Way's galactic halo carry signatures of previous stellar generations, traces of carbon, oxygen, and iron that speak of supernovae explosions and neutron star collisions that enriched the interstellar medium before these ancient suns were born. The metallicity levels observed in these primitive stars suggest the universe had already undergone multiple cycles of star formation, stellar death, and chemical enrichment by the time they formed, supposedly less than 1 billion years after the Big Bang. The chemical archaeology grows more puzzling when astronomers measure the abundance ratios of different elements in ancient stellar atmospheres. Alpha elements like oxygen and magnesium produced primarily in massive star supernovae, appear in ratios that suggest extended periods of chemical evolution involving multiple generations of stellar death and rebirth. The iron-to-alpha element ratios observed in metal-poor stars indicate a complex history of nucleosynthesis that requires far more time than standard cosmological models provide for early chemical enrichment. Globular clusters, ancient stellar cities containing hundreds of thousands of stars born from the same molecular cloud, show internal chemical variations that should be impossible if they formed in a single burst of star formation. Multiple stellar populations within individual globular clusters display different abundances of light elements like sodium and oxygen, suggesting that these clusters experience several episodes of star formation fed by material polluted by previous generations of cluster stars. This internal chemical evolution requires time for the first stellar generation to live, die, and enrich the cluster's remaining gas before the second generation could form. Only took several billion years longer than expected for the universe to learn chemistry. Only required multiple stellar generations to die and scatter their enriched ashes before the oldest surviving stars were born. Only needed the cosmos to forget that its first chapter was supposed to be written in pure hydrogen and helium. Like cosmic alchemists working across deep time, successive generations of stars transmuted light elements into heavy ones through nuclear fusion in their cores, forging carbon from helium, oxygen from carbon, and iron from silicon in a process that operates over billions of years. When these stellar furnaces exhausted their nuclear fuel, they scattered their enriched contents through supernovae explosions that seeded the interstellar medium with metals, creating the raw material for subsequent generations of chemically enriched stars, the most ancient white dwarf stars. The cooling remnants of stars that died billions of years ago show atmospheric compositions that reveal their progenitor stars' chemical histories. These stellar corpses have been cooling for so long that their surface temperatures provide independent age estimates for the galaxy's oldest stellar populations. Some white dwarfs appear to have cooling ages that approach or exceed the supposed age of the universe, requiring either modification of stellar evolution theory or acknowledgement that the cosmos is older than current models suggest. Neutron-star collision events, responsible for creating elements heavier than iron through rapid neutron capture processes, leave distinctive chemical fingerprints in subsequent generations of stars formed from the enriched debris. The abundance patterns of rare Earth elements and platinum group metals observed in metal-poor stars suggest that neutron-star mergers were already occurring in the early universe, enriching the interstellar medium with R-process elements. But these merger events require binary neutron star systems that take billions of years to spiral inward and collide under gravitational wave radiation. The chemical evolution of galaxies proceeds through what astronomers call the closed box model, where star formation and chemical enrichment occur within isolated galactic systems without significant exchange of material with the intergalactic medium. Yet observations of chemical abundance gradients within galaxies, where metallicity decreases with distance from galactic centers, suggest that galaxies have been chemically evolving for much longer than their supposed formation times would permit. Perhaps the universe began its chemical education long before the epoch we recognize as the beginning of star formation, in some prior phase where different physical conditions allowed rapid element synthesis through processes we haven't yet identified. Perhaps what we observe as the first generation of metal-enriched stars represents the survivors of much earlier stellar populations whose existence is hidden in the cosmic microwave background's patterns of temperature and polarization. Spectroscopic surveys of thousands of ancient stars reveal chemical abundance patterns that show remarkable consistency across vast regions of the galaxy, suggesting that early chemical enrichment occurred on scales large enough to homogenize the interstellar medium across kiloparsecs. This large-scale chemical mixing requires gravitational and hydrodynamic processes, operating over timescales much longer than standard galaxy formation models accommodate. The lithium problem adds another layer to the metallicity paradox. Big Bang nucleosynthesis should have produced specific amounts of lithium-7 during the first few minutes after the initial expansion. Yet observations of the most metal-poor stars show lithium abundances significantly lower than theoretical predictions. This discrepancy suggests either that our understanding of primordial nucleosynthesis is incomplete, or that these supposedly pristine stars have been contaminated by material from previous stellar generations that somehow destroyed primordial lithium. Hypervelocity stars. Traveling so fast they will eventually escape the galaxy's gravitational pull, carry chemical signatures that reveal their birthplaces in the galactic center or bulge regions. Some of these high-velocity objects show metallicities consistent with formation in chemically evolved environments, yet their trajectories suggest they were ejected from the galactic center billions of years ago when the Milky Way was supposedly much younger and less chemically enriched. The chemical memories preserved in ancient stellar atmospheres continue to challenge our understanding of cosmic chronology. Each absorption line in their spectra representing elements forged in stellar cores and scattered through supernovae explosions that supposedly occurred before there was time for such processes to operate. The metallicity paradox whispers of a universe that began its chemical evolution much earlier than we imagine, in epochs hidden behind the cosmic microwave background's luminous veil. Modern stellar archaeology reveals the galaxy's chemical history written in the atmospheric compositions of its oldest members, each star a fossil record of the interstellar medium from which it formed. Yet these stellar fossils consistently tell stories of chemical enrichment that began earlier and proceeded faster than standard models of cosmic evolution permit, as if the universe had already been practicing stellar alchemy for eons before the first stars we can observe began to shine. In the deepest reaches of space, where galaxy clusters drift like luminous cities across cosmic voids, astronomers discover the remnants of gravitational choreography that speaks of dance steps rehearsed over impossible spans of time. Ancient galaxy mergers reveal collision histories written in stellar streams and tidal tales, gravitational signatures that require billions of years to choreograph, yet appear in systems that supposedly formed recently in cosmic terms. These merger remnants preserve the memory of gravitational encounters that began when the universe was supposedly too young for such massive structures to exist. The Milky Way itself bears the scars of ancient collisions. Stellar streams wrapped around our galaxy like ribbons of stars torn from smaller companions during close gravitational encounters. The Sagittarius dwarf galaxy continues its slow dissolution, leaving a trail of stars that encircles our galactic disk multiple times. The result of repeated passages through the Milky Way's gravitational field over billions of years. Computer simulations suggest this ongoing merger began more than 8 billion years ago, requiring both galaxies to have achieved significant mass and structure when the universe was supposedly less than half its current age. Galaxy archaeology reveals even more ancient merger events preserved in the stellar halo surrounding our galaxy. Fossil remnants of dwarf galaxies that were completely disrupted and accreted billions of years ago. These stellar streams show chemical abundance patterns distinct from native Milky Way stars, evidence of independent chemical evolution in their parent galaxies before the merger process began. The diversity of chemical signatures suggests our galaxy assembled from numerous smaller systems over extended periods, a hierarchical buildup requiring more time than standard models of galaxy formation provide. Major galaxy mergers, like those that created the massive elliptical galaxies dominating rich galaxy clusters, operate on timescales that challenge cosmic chronology. When two large spiral galaxies approach each other, their initial gravitational encounter begins when they are separated by several million light-years, still beyond the virial radius where their dark matter halos overlap. The merger process unfolds through multiple stages of approach: tidal interaction, core passage, and final coalescence. with the entire sequence requiring several billion years to complete even after the galaxies first begin to gravitationally influence each other. Numerical simulations of galaxy mergers reveal the intricate gravitational dynamics involved when massive stellar systems interact. During close passages, tidal forces stretch both galaxies, pulling streams of stars and gas into long filamentary structures that can extend for hundreds of thousands of light years from the main galactic bodies. These tidal tails persist for billions of years after the merger event, slowly fading as stellar orbits randomize and the merged system relaxes into a new equilibrium configuration. Only took the universe twice as long as it admits to perfect its gravitational choreography, only required dark matter halos to grow massive enough to capture and hold galaxies before the galaxies themselves supposedly existed. Only needed billions of years of rehearsal time for merger events that appear complete in systems formed when the cosmos was supposedly young and simple, like cosmic ballet dancers locked in gravitational embrace. Merging galaxies orbit their common center of mass in ever-tightening spirals as dynamical friction dissipates their orbital energy. The process creates spectacular displays of tidal forces, with stellar streams and bridges connecting the galaxies during their closest approaches. These gravitational performances leave lasting signatures in the final merged system, including shells of stars at large radii and kinematically distinct stellar components in the galactic core. The Virgo cluster, the nearest major galaxy cluster to the Milky Way, contains numerous examples of ongoing and ancient merger activity among its member galaxies. M87, the cluster's central giant elliptical galaxy, shows multiple shells and jets that speak of recent accretion events, while its enormous size suggests it formed through the merger of dozens of smaller galaxies over extended periods. The cluster's gravitational environment has been facilitating galaxy interactions for billions of years. Yet, it formed when the universe was supposedly too young for such massive structures. Deep imaging of galaxy cluster cores reveals intra-cluster stellar populations, stars that were stripped from their parent galaxies during close encounters and now orbit freely within the cluster's gravitational potential. These orphan stars make up a significant fraction of the cluster's total stellar mass, indicating that tidal stripping and galaxy harassment have been operating for extended periods. The amount of intra-cluster starlight observed requires billions of years of galaxy interactions within already mature cluster environments. Perhaps the gravitational encounters we observe today began in a much earlier epoch, when cosmic expansion rates were different and galaxy interaction timescales operated under different physical conditions. Perhaps the merger histories written in stellar streams and tidal features represent the final chapters of gravitational stories that began when the universe was already ancient in ways we don't yet recognize. Fossil galaxy groups embedded within larger clusters preserve evidence of complete merger sequences that occurred before cluster assembly began. These systems show relaxed, spherical distributions of galaxies around a central dominant elliptical, configurations that require several billion years to achieve through gravitational relaxation processes. Yet their presence within larger clusters suggests they formed as independent systems and were later accreted intact, implying a complex hierarchy of structure formation operating over extended timescales. The morphology-density relation observed in galaxy clusters, where elliptical galaxies dominate dense cluster cores, while spiral galaxies are more common in cluster outskirts, reflects the cumulative effects of gravitational encounters over cosmic time. Galaxies falling into cluster cores experience ram pressure stripping of their gas content and tidal harassment from close encounters with cluster neighbors. These environmental processes transform spiral galaxies into ellipticals through mechanisms that operate slowly even by astronomical standards. Compact galaxy groups, small associations of galaxies in which members are separated by only a few galaxy diameters, provide natural laboratories for studying gravitational interactions in progress. These systems show clear evidence of ongoing tidal stripping, star formation triggered by gravitational encounters, and the gradual merger of group members into a single massive galaxy. The diversity of interaction signatures observed in compact groups suggests they represent different stages of a merger sequence that spans billions of years. Ultra-diffuse galaxies, systems with extremely low surface brightness spread across enormous areas, may represent the end products of extreme tidal stripping during galaxy encounters. These ghostly systems retain only a fraction of their original stellar content, with the rest scattered into tidal streams or completely dispersed. Their current properties suggest they survived gravitational encounters that began billions of years ago when their progenitor galaxies were more compact and massive. The archaeological record preserved in merger remnants continues to reveal gravitational histories that began earlier and proceeded more slowly than cosmic chronology permits. Each tidal stream represents a chapter in an ongoing story of gravitational interaction. While the final merged systems show the cumulative results of processes that require extended rehearsal time, the gravitational choreography observed in galaxy clusters speaks of dance steps learned over timescales that stretch the universe's supposed age beyond its conventional limits. Modern photometric surveys reveal the full extent of tidal debris around nearby galaxies. Stellar streams and shells that trace orbital histories extending billions of years into the past. These gravitational fossils preserve detailed information about merger events, including the masses and orbital parameters of the disrupted companions. Yet the number and complexity of merger features observed around typical galaxies suggest they experienced rich interaction histories that began when the universe was supposedly too young for significant structure formation. The dance continues today in galaxy clusters across the observable universe. Gravitational encounters proceeding with cosmic patience through collision sequences that will require billions of years to complete. Each merger event adds new chapters to the gravitational archaeology of the cosmos, contributing to an ever-growing record of interactions that seem to require more rehearsal time than the universe has supposedly provided. Beyond the familiar constellations and the gentle spiral arms of our own galaxy, something massive pulls everything in the local universe toward a destination that remains hidden behind dust clouds and galaxy clusters. The Great Attractor exerts its gravitational influence across hundreds of millions of light-years, drawing the Milky Way, Andromeda, and thousands of neighboring galaxies in a cosmic procession toward a region of space so dense with matter that it defies explanation within standard models of structure formation. This gravitational anomaly lies roughly 250 million light-years away in the direction of the constellation Hydra, hidden behind the plane of our own galaxy where interstellar dust blocks optical observations. Radio and infrared astronomy reveal a concentration of galaxy clusters and superclusters that collectively outweigh our local group by factors that would make gravitational physicists pause in their calculations. The mass required to generate the observed peculiar velocities of galaxies suggests a structure so large and massive that it should not exist given the universe's supposed age. Peculiar velocity measurements reveal that our local group of galaxies moves through space at roughly 600 kilometers per second relative to the cosmic microwave background, a motion that cannot be explained by the gravitational influence of nearby visible matter alone. This cosmic flow carries us toward the Great Attractor, along with thousands of other galaxies in what astronomers call the local supercluster's bulk motion. The gravitational acceleration required to achieve these velocities implies the attracting mass began influencing galaxy motions billions of years ago. Behind the Great Attractor itself lies an even larger structure called the Shapley supercluster, a concentration of galaxy clusters so massive that it may be responsible for our local group's motion through an additional gravitational pull extending across a billion light-years of space. The combined gravitational influence of these nested structures creates a hierarchy of cosmic flows that operate on scales approaching the horizon distance, requiring gravitational systems that have been organizing matter since the universe was supposedly in its infancy. The cosmic web of galaxy filaments and clusters shows preferential alignment toward these massive attractors, as if the large-scale structure of the universe has been shaped by gravitational influences operating from very early times. Galaxy surveys reveal that superclusters and void boundaries orient themselves along directions pointing toward the Great Attractor and similar massive structures, suggesting that these gravitational anchors have been organizing cosmic architecture for most of the universe's history. Only took several billion years longer than expected for gravity to build structures massive enough to influence galaxy motions across cosmic distances. Only required dark matter concentrations exceeding theoretical limits to create attractors invisible to direct observation. Only needed the patience of empty space to allow gravitational influences to propagate across scales approaching the observable universe, like rivers flowing toward unseen oceans. Galaxy streams converge along filamentary highways that lead toward these massive gravitational concentrations. The Norma cluster, the Centaurus cluster, and dozens of other rich galaxy groups participate in this cosmic convergence, their collective gravitational field creating a basin of attraction that has been drawing in surrounding matter for billions of years. The scale of this gravitational architecture exceeds what simulations can produce within standard cosmological timelines. Redshift surveys, mapping the three-dimensional positions of galaxies, reveal coherent bulk flows extending across hundreds of millions of light-years, with galaxy peculiar velocities showing systematic patterns that point toward regions of enhanced matter density. These large-scale flows require gravitational potentials deep enough to accelerate galaxies to significant fractions of their total velocities over cosmic time, implying that the attracting structures achieved considerable mass concentrations early in the universe's evolution. The cosmic microwave background itself bears subtle imprints of these large-scale gravitational structures, temperature fluctuations that correspond to the gravitational potentials of massive attractors. The integrated Sachs-Wolf effect creates hot and cold spots in the background radiation as photons climb out of or fall into gravitational wells associated with evolving large-scale structure. The amplitude of these temperature signatures suggests that significant gravitational potentials were already present when the universe became transparent to radiation. Perhaps these massive attractors represent the gravitational memory of structure formation processes that began in a much earlier epoch, density fluctuations that achieved nonlinear growth before the expansion phase we recognize as the Big Bang. Perhaps the Great Attractor and similar structures preserve information about cosmic initial conditions that required extensive time to establish. Gravitational seeds planted in some prior phase of cosmic evolution, numerical simulations attempting to reproduce the observed large-scale structure struggle to generate attractors as massive as those indicated by galaxy peculiar velocities within the standard cosmological framework. The simulations require either modified initial conditions with enhanced power on large scales or extended periods of structure growth beyond what the standard model permits. The gravitational influence of these attractors appears to extend back to epochs when the universe was supposedly too young for such massive structures. The Laniakea supercluster, a recently mapped gravitational domain spanning 500 million light-years, represents the sphere of influence within which the Great Attractor and associated structures dominate galaxy motions. This vast region contains tens of thousands of galaxies organized into a network of filaments and nodes, all participating in coherent flows toward the region's gravitational center. The scale and organization of Laniakea suggest it has been evolving as a gravitational system for most of cosmic history. Galaxy. Peculiar velocities within the zone of influence show systematic patterns that trace back billions of years, orbital histories that require the attracting structures to have maintained stable gravitational fields over extended periods. The coherence of these motions across such vast scales implies that the Great Attractor achieved its current mass and gravitational influence much earlier than standard structure formation models predict. Cold, dark matter simulations produce cosmic web structures that qualitatively resemble the observed large-scale distribution of galaxies, but they consistently underpredict the masses and gravitational influences of the largest structures. The Great Attractor and similar massive concentrations appear to require either non-standard dark matter properties or modified cosmological parameters that allow enhanced structure growth on large scales. The gravitational archaeology preserved in galaxy streaming motions continues to reveal evidence of massive structures that began influencing cosmic evolution much earlier than expected. Each peculiar velocity measurement provides information about gravitational fields that have been accelerating galaxies for billions of years, requiring attracting masses that achieved significant concentration when the universe was supposedly young and smooth. Modern surveys attempting to map the full extent of the Great Attractor's influence find that its gravitational reach extends far beyond initial estimates, affecting galaxy motions across a significant fraction of the observable universe. The discovery that such massive structures can influence cosmic evolution on nearly horizon-scale distances suggests that gravitational organization began operating in the early universe much sooner and more efficiently than standard models permit. The silent pull continues today, drawing galaxies across hundreds of millions of light-years in a cosmic migration that will require billions of years to complete. The Great Attractor remains patient and persistent, its gravitational influence reaching across space and time to organize matter on scales that challenge our understanding of how long such massive structures require to form and establish their gravitational dominance over cosmic evolution. Beneath the fabric of space-time itself, in the quantum vacuum that fills every cubic centimeter of apparently empty space, energy fluctuations persist with a constancy that suggests the universe has been humming with activity far longer than conventional cosmology acknowledges. The zero-point energy field represents the irreducible minimum energy state of quantum fields, a background of virtual particle pairs constantly appearing and annihilating in timescales shorter than measurement can detect. Yet the cumulative effect of these quantum fluctuations may preserve information about cosmic states that preceded the expansion epoch we recognize as the beginning. Quantum field theory predicts that the vacuum contains energy densities so enormous that they should curve space-time into impossibly small radii, creating a universe that collapses before it can expand. This cosmological constant problem represents one of the most severe fine-tuning issues in modern physics, requiring the vacuum energy to be suppressed by factors approaching 10 circumflex 120 to match observations of cosmic acceleration. The precise cancellation needed to achieve the observed vacuum energy density suggests a universe that has had extensive time to reach this delicate equilibrium. Casimir effect measurements demonstrate that quantum vacuum fluctuations exert measurable forces between closely spaced conducting plates, confirming that the apparently empty space contains real physical energy. These forces arise from the suppression of certain wavelength modes between the plates, creating a pressure differential that pushes the conductors together. The existence of measurable vacuum forces implies that quantum fields have been maintaining their zero-point oscillations since whatever epoch established the current physical constants. Virtual particle pairs in the quantum vacuum carry momentum and energy, contributing to what physicists call vacuum polarization around massive objects and strong electromagnetic fields. Near black hole event horizons, vacuum fluctuations can become real particles through the Hawking radiation process, with one member of a virtual pair falling into the black hole while the other escapes to infinity. This particle creation from vacuum energy requires quantum fields that have been sustaining their fluctuation spectra across cosmic time. The quantum vacuum exhibits structure on multiple scales, from Planck length fluctuations in space-time geometry to macroscopic coherent states that may influence cosmic evolution. Inflation theory attempts to explain cosmic flatness and homogeneity by invoking a period of exponential expansion driven by vacuum energy in a scalar field. Yet the initial conditions required for inflation to begin and end at precisely the right moments suggest a universe that was already fine-tuned before the inflationary epoch commenced. Only took the universe several cosmic ages longer than it admits to learn how to balance quantum vacuum energy to within 1 part in 10 circumflex 120. Only required virtual particles to maintain their patient dance of creation and annihilation since before space and time achieved their current configuration. Only needed the quantum vacuum to preserve its zero-point hum across phases of cosmic evolution that remain hidden behind the curtain of the Big Bang. Like a cosmic orchestra tuning its instruments across scales from subatomic to galactic, quantum fields maintain their characteristic frequencies throughout all regions of space and time. The electromagnetic field sustains its zero-point oscillations at every possible wavelength, while other quantum fields contribute their own signatures to the vacuum energy spectrum. This quantum symphony has been playing since whatever epoch established the fundamental constants that determine field properties and interaction strengths. Vacuum fluctuations contribute to the anomalous magnetic moment of elementary particles, tiny corrections to their gyromagnetic ratios that arise from virtual particle interactions. These quantum corrections have been measured to extraordinary precision, confirming theoretical predictions to more than 10 decimal places. The stability of these quantum contributions across cosmic time suggests that the vacuum state has maintained its properties since the earliest moments, when particles acquired their masses and interaction strengths. Dark energy, the mysterious component driving cosmic acceleration, may represent a small imbalance in the quantum vacuum energy density. Current observations indicate that dark energy contributes roughly 68% of the universe's total energy budget, yet its origin and properties remain completely unknown. If dark energy arises from vacuum fluctuations, its current density suggests that quantum fields achieved their present configuration much earlier than standard cosmology permits. Perhaps the quantum vacuum preserves information about pre-Big Bang states, maintaining field configurations that originated in some prior phase of cosmic evolution when different physical laws governed space-time geometry and particle interactions. Perhaps the zero-point energy field represents a kind of cosmic memory, quantum states that survived whatever transition brought our observable universe into existence and continue to influence cosmic evolution through their cumulative gravitational effects. Spontaneous symmetry, breaking in quantum field theory, provides mechanisms by which the vacuum state can evolve from symmetric configurations to states with lower energy but broken symmetries. The Higgs mechanism, responsible for giving mass to elementary particles, operates through such vacuum phase transitions. The current vacuum state may represent the end result of multiple symmetry-breaking events that occurred over extended periods of cosmic evolution. String theory and other quantum gravity approaches suggest that space-time itself emerges from more fundamental quantum degrees of freedom, with the familiar 3 spatial dimensions and 1 time dimension arising as low-energy approximations to higher dimensional quantum geometries. These emergent space-time scenarios imply that our observable universe represents a particular phase in the evolution of more fundamental quantum systems that may have been evolving for much longer than conventional cosmology recognizes. Quantum entanglement between vacuum fluctuations creates correlations that extend across arbitrary distances, connecting regions of space through non-local quantum relationships that transcend classical space-time boundaries. These vacuum entanglement networks may preserve information about cosmic initial conditions, maintaining quantum correlations that originated when the universe was much smaller and denser than current models assume. The measurement problem in quantum mechanics raises questions about when and how quantum superposition states collapse into definite classical configurations on cosmic scales. The transition from quantum to classical behavior may have required extended periods for decoherence processes to establish the classical space-time geometry we observe today. This quantum to classical transition could have begun much earlier than the epoch we associate with classical Big Bang cosmology. Vacuum decay scenarios in quantum field theory suggest that our current vacuum state may be metastable, capable of tunneling to lower energy configurations through quantum barrier penetration. If the universe has already survived multiple vacuum decay events, each transition could have reset cosmic evolution while preserving certain quantum field properties from previous phases. The apparent stability of our current vacuum state may reflect extensive evolutionary time spent in metastable configurations. The persistent hum of quantum vacuum fluctuations continues today in every region of space, maintaining the zero-point energy that may hold memories of cosmic states that preceded observable history. Each virtual particle pair carries information about field configurations that have been sustained across whatever transitions brought the universe from its primordial quantum state to the classical space-time geometry that hosts galaxies. Stars, and the patient observations of quantum physicists measuring vacuum forces in laboratory experiments. Across the vast distances that separate galaxies, photons lose energy in ways that may extend far beyond the simple cosmological redshift predicted by expanding space-time models. The phenomenon known as tired light suggests that electromagnetic radiation experiences energy dissipation during its journey through intergalactic space, gradually shifting toward longer wavelengths through interactions with cosmic media or fundamental processes that operate over astronomical distances. This gradual energy loss could account for portions of the redshift observed in distant galaxies, potentially indicating that the universe is older and larger than expansion-based distance estimates suggest. Fritz Zwicky first proposed tired light mechanisms in the 1920s as an alternative explanation for galactic redshift observations, suggesting that photons might scatter off intergalactic matter or lose energy through unknown physical processes during their cosmic journeys. While mainstream cosmology adopted expanding universe models to explain redshift distance relationships, tired light scenarios continue to attract theoretical interest because they could resolve several cosmological puzzles, including the apparent youth of the universe compared to the ages of its oldest stellar populations. Compton, scattering interactions between photons and free electrons in the intergalactic medium, provide one mechanism by which electromagnetic radiation could lose energy during cosmic propagation, although the cross-section for these interactions is extremely small. The cumulative effect over billions of light-years might produce measurable energy loss. The intergalactic medium contains enough ionized gas to support significant Compton scattering, particularly in the warm-hot intergalactic medium that fills the cosmic web filaments connecting galaxy clusters. Plasma physics in the intergalactic medium offers additional mechanisms for photon energy dissipation through wave-particle interactions and plasma instabilities that develop over cosmic scales. Electromagnetic waves propagating through weakly ionized gas can couple to plasma oscillations, transferring energy to particle motions through various resonance phenomena. These plasma processes operate continuously throughout intergalactic space, providing a persistent mechanism for photon energy loss that accumulates over cosmic distances. The cosmic microwave background radiation itself may experience tired light effects during its journey from the surface of last scattering to present-day observers. If photons lose energy through fundamental processes beyond cosmological redshift, the observed temperature of the microwave background could reflect both expansion cooling and additional energy dissipation mechanisms. This could partially explain the apparent maturity of structures encoded in the background radiation's temperature fluctuations. Only took light 13 billion years longer than expected to get properly tired during its cosmic commute. Only required photons to forget portions of their original energy through mechanisms that remain invisible to direct detection. Only needed the universe to provide additional time for electromagnetic radiation to sample every possible interaction during its journey across cosmic distances, like cosmic marathoners gradually slowing during an impossibly long race. Photons may experience fatigue effects that accumulate imperceptibly over the vast distances separating galaxies and galaxy clusters. Each interaction with intergalactic particles, magnetic fields, or quantum vacuum fluctuations could extract tiny amounts of energy from electromagnetic radiation, shifting photon frequencies toward the red end of the spectrum through mechanisms distinct from Doppler shifting and expanding spacetime. Variable speed of light theories suggest that fundamental constants may evolve over cosmic time, with the speed of light potentially decreasing as the universe ages. If electromagnetic radiation traveled faster in the early universe, photons emitted by distant galaxies would have required less time to reach Earth than standard models predict, implying that these galaxies are older than their redshift-based distance estimates suggest. This could resolve the apparent conflict between galactic ages and cosmic age derived from expansion models. Quantum vacuum interactions provide another potential mechanism for photon energy loss over cosmic distances. Virtual particle pairs in the quantum vacuum could absorb small amounts of energy from propagating electromagnetic radiation through higher-order quantum electrodynamic processes. While these interactions are extremely weak, their cumulative effect over billions of light-years might contribute measurably to the observed redshift of distant galaxies. Perhaps tired light effects operate alongside cosmological expansion, with both mechanisms contributing to the redshift observations that form the foundation of modern cosmology. Perhaps the universe expands more slowly than current models suggest, requiring tired light processes to account for portions of the observed redshift. This hybrid scenario could reconcile expansion-based age estimates with observations of apparently ancient stellar populations and mature galactic structures. Gravitational interactions with dark matter concentrations along photon propagation paths could contribute to energy loss through gravitational redshift effects that accumulate over cosmic distances. As electromagnetic radiation climbs out of gravitational potential wells associated with dark matter halos, it loses energy and shifts toward longer wavelengths. The cumulative effect of climbing out of numerous potential wells during cosmic propagation could supplement the redshift produced by cosmological expansion. Electromagnetic field interactions with cosmic magnetic fields threading intergalactic space provide additional mechanisms for energy transfer from propagating photons to the magnetized plasma-filling cosmic web filaments. Faraday rotation and other magnetoplasma effects could gradually drain energy from electromagnetic radiation over cosmic distances, contributing to observed redshift through processes distinct from geometric expansion effects. Alternative gravity theories, including modified Newtonian dynamics and scalar tensor gravitational models, predict deviations from standard general relativity that could affect photon propagation over cosmic distances. These theories often include additional gravitational fields or modified dispersion relations for electromagnetic radiation that could contribute to energy loss during cosmic propagation, supplementing or replacing expansion-based redshift mechanisms. The surface brightness dimming observed in distant galaxies follows a relationship with redshift that may provide observational tests for tired light mechanisms. Pure cosmological expansion predicts specific surface brightness evolution that differs from tired light predictions. Although distinguishing between these scenarios requires extremely precise photometry of galaxies across a wide range of distances and wavelengths, spectral line-width evolution in distant galaxies could offer additional observational signatures of tired light processes. If photon energy loss mechanisms operate differently at different wavelengths, spectral lines from distant sources might show broadening or shifting patterns distinct from those predicted by cosmological expansion alone. These spectroscopic effects could provide direct evidence for energy dissipation during electromagnetic propagation. Modern observations of distant supernovae, gamma-ray bursts, and quasars provide increasingly precise tests of photon propagation models over cosmic distances. The consistency of standard candle brightnesses and spectral properties across different redshift ranges places strong constraints on tired light mechanisms. Yet, subtle deviations from expansion-only models might still be detectable with next-generation astronomical instruments. The patient journey of electromagnetic radiation across cosmic space continues today, with photons from the most distant observable galaxies carrying information about energy loss processes that operate over scales approaching the horizon distance. Each photon that reaches Earth bears the accumulated effects of its cosmic journey, preserving in its wavelength and polarization the signature of every interaction encountered during billions of years of propagation through the evolving intergalactic medium. Tired light remains a quiet possibility in cosmic distance measurements, a reminder that the universe might provide more time and space for its contents to evolve than expansion-based models currently suggest. The gradual reddening of distant starlight whispers of journeys that may have required longer than expected, electromagnetic radiation growing weary during travels across a cosmos that extends further into space and deeper into time than conventional wisdom permits. The expansion of space itself accelerates through cosmic history in patterns that suggest the universe has been experimenting with different expansion rates for much longer than standard models accommodate. Dark energy, comprising roughly 68% of the cosmic energy budget, drives this acceleration through mechanisms that remain completely mysterious to theoretical physics. Yet the evolution of the expansion rate shows variations and transitions that appear to require extensive calibration time, as if the universe spent eons learning how to balance the competing influences of matter, radiation, and vacuum energy. Type Ia supernovae observations across multiple redshift ranges reveal that cosmic expansion was decelerating during the matter-dominated epoch, but began accelerating roughly 5 billion years ago when dark energy started to dominate the universe's energy density. This transition from deceleration to acceleration represents a fundamental change in cosmic evolution, yet the smoothness of the transition suggests it represents the culmination of processes that had been developing for much longer than the supposed age of the universe at that epoch. The equation of state parameter for dark energy, denoted W, determines how dark energy density evolves as the universe expands. Current observations suggest W remains close to -1, corresponding to a cosmological constant, but precision measurements hint at possible evolution in this parameter over cosmic time. If dark energy properties change, the expansion history becomes more complex, potentially requiring longer timescales for the universe to achieve its current acceleration rate. Baryon acoustic oscillations, characteristic length scales imprinted in the cosmic microwave background and preserved in galaxy correlation functions, provide standard rulers for measuring cosmic expansion across different epochs. These acoustic features show systematic patterns that trace the universe's expansion history from the epoch of recombination to the present day. Yet the consistency of these patterns across cosmic time suggests that expansion processes achieved remarkable stability much earlier than expected. The Hubble tension, a persistent discrepancy between expansion rate measurements using different methods and distance scales, may indicate that cosmic expansion operates differently on various scales or epochs. Local measurements based on Cepheid variable stars and supernovae yield higher Hubble constant values than estimates derived from cosmic microwave background observations. This tension could suggest that expansion rates have been evolving in ways not captured by standard cosmological models, only took the universe several billion years longer than it admits to learn the proper balance between matter and vacuum energy needed for smooth acceleration. Only required dark energy to maintain precisely the right equation of state to avoid either rapid collapse or runaway expansion. Only needed cosmic time to allow expansion parameters to evolve gradually toward their current values through mechanisms that remain completely unknown. like a cosmic engine gradually shifting gears across deep time. The universe transitions between different expansion regimes as various energy components dominate its evolution. During the radiation-dominated epoch, photons and relativistic particles drove rapid early expansion. The matter-dominated epoch saw expansion decelerate as gravitational attraction from dark matter and ordinary matter slowed cosmic growth. The current dark energy-dominated epoch experiences accelerating expansion as vacuum energy overcomes gravitational deceleration. Modified gravity theories attempt to explain cosmic acceleration without invoking mysterious dark energy, suggesting that gravitational physics operates differently on cosmic scales or in low acceleration regimes. These theories often predict expansion histories that differ subtly from lambda CDM cosmology, potentially requiring longer timescales for the universe to achieve its current expansion properties. The gradual emergence of modified gravitational effects could explain why acceleration began relatively recently in cosmic history. Quintessence models propose that dark energy arises from a slowly evolving scalar field rather than a pure cosmological constant. These dynamic dark energy scenarios predict that the expansion rate should show more complex evolution over cosmic time, with periods of acceleration and deceleration depending on the scalar field's potential energy function. The fine-tuning required for quintessence fields to produce observed expansion. History suggests these fields have been evolving for much longer than standard cosmology permits. Perhaps cosmic acceleration represents the latest phase in a cyclical process that has been operating for much longer than the apparent age of the universe. Perhaps dark energy density oscillates over cosmic cycles, driving periods of acceleration and deceleration that repeat on timescales longer than individual expansion phases. This could explain why the current acceleration epoch began at a seemingly arbitrary moment in cosmic history. The coincidence problem in cosmology asks why dark energy and matter densities happen to be comparable at the present epoch, despite evolving at different rates throughout cosmic history. Matter density decreases as the universe expands, while dark energy density remains approximately constant. The fact that these densities crossed over to make dark energy dominant relatively recently seems to require remarkable timing, unless the universe is much older than current estimates suggest. Phantom dark energy scenarios, where WW-1 predict that dark energy density actually increases as the universe expands, leading to a big rip scenario where expansion accelerates so rapidly that it eventually tears apart all gravitationally bound structures. The apparent stability of our current cosmic expansion rate against phantom behavior suggests that dark energy properties have been carefully calibrated over extended periods to avoid catastrophic outcomes. Early dark energy models attempt to resolve cosmological tensions by invoking significant dark energy contributions during earlier cosmic epochs, particularly around the time of recombination when the cosmic microwave background formed. These models require dark energy to have been present and influential much earlier than standard scenarios suggest, implying that acceleration processes have been operating throughout most of cosmic history. The cosmic web of galaxy filaments and voids shows structural properties that depend sensitively on the expansion history and dark energy properties. N-body simulations attempting to reproduce observed large-scale structure must carefully tune expansion parameters to match galaxy clustering statistics and void size distributions. The precision required for these matches suggests that cosmic expansion has been following a finely calibrated trajectory for much longer than expected. String theory and extra-dimensional models propose that our observable four-dimensional space-time represents a lower dimensional slice of higher dimensional space, with dark energy arising from the geometry and dynamics of extra dimensions. These scenarios often predict complex evolution of expansion rates as extra-dimensional geometries evolve, potentially requiring much longer timescales for stabilization than conventional cosmology accommodates. Observational surveys measuring cosmic expansion rates across different redshift ranges continue to reveal subtle deviations from simple models. Systematic patterns that suggest the expansion history contains more complexity than lambda CDM cosmology captures. Each precision measurement of distant supernovae, baryon acoustic oscillations, and gravitational lensing time delays adds constraints to expansion models, while revealing residual tensions that point toward longer cosmic evolution timescales. The patient acceleration of cosmic expansion continues today, driven by dark energy processes that maintain their mysterious influence across scales from galactic clusters to the cosmic horizon. Each measurement of cosmic distances and expansion rates provides another clue to the evolution of space-time itself, revealing an expansion history that appears to require more time and more complex dynamics than standard models currently permit. Modern cosmological observations push measurements of cosmic expansion to ever higher precision, seeking to understand whether dark energy represents a fundamental property of space-time or an evolving field that has been guiding cosmic evolution for much longer than the universe's apparent age would suggest. The accelerating mystery of dark energy whispers of cosmic processes that began their patient work in epochs hidden behind the luminous veil of the cosmic microwave background. In the extreme gravitational fields that existed during the universe's earliest moments, quantum fluctuations could collapse directly into black holes without requiring stellar core collapse or accretion processes. These primordial black holes, if they formed in significant numbers, would carry information about physical conditions during epochs so early that no other observational probe can reach them. Yet the mass spectrum and abundance of primordial black holes that current observations seem to require suggests formation mechanisms that operated when the universe was supposedly too young and simple for such complex gravitational collapse events. Primordial black holes could form whenever density fluctuations exceeded critical thresholds during the radiation-dominated epoch, compressing matter to such extreme densities that gravitational collapse became inevitable despite radiation pressure. The critical density threshold for black hole formation depends on the equation of state and pressure gradients in the early universe, parameters that may have been very different during pre-Big Bang phases of cosmic evolution. The formation of primordial black holes requires density contrasts that seem inconsistent with the smooth initial conditions inferred from cosmic microwave background observations. Hawking radiation causes black holes to evaporate over timescales that depend inversely on their mass, with smaller black holes evaporating faster than larger ones. Primordial black holes with masses below roughly 10 circumflex 15 grams would have already evaporated through Hawking radiation by the present epoch, leaving only larger primordial black holes as potential dark matter candidates. The mass spectrum of surviving primordial black holes preserves information about formation conditions in the early universe, requiring density fluctuation amplitudes that challenge standard inflation models. Gravitational wave observations by LIGO and Virgo detect black hole merger events with masses and merger rates that may include contributions from primordial black hole populations. Some of the observed black hole masses fall within ranges that are difficult to explain through stellar evolution alone, particularly black holes in the mass gap region where stellar core collapse should not produce compact objects. These intermediate mass black holes could represent survivors from primordial formation epochs. The abundance of primordial black holes required to explain dark matter or gravitational wave observations implies formation rates that seem inconsistent with standard models of early universe evolution. Density fluctuations large enough to produce significant primordial black hole populations should also leave observable signatures in the cosmic microwave background. Yet no such signatures are definitively detected. This suggests either that primordial black hole formation occurred during pre-recombination epochs not directly observable, or that formation mechanisms operated differently than current theories predict. only took the universe several cosmic epochs longer than expected to learn how to collapse quantum fluctuations into gravitational singularities, only required density contrasts far exceeding cosmic microwave background fluctuations to generate black holes before stars existed to provide the conventional formation mechanism, only needed space-time itself to achieve curvatures approaching Planck scales when the cosmos was supposedly smooth and homogeneous. Like gravitational seeds planted in the quantum foam of the early universe, primordial black holes preserve information about physical conditions that existed before any other structures formed. Their event horizons isolate classical space-time regions from the quantum gravitational regime, creating information storage systems that have been accumulating entropy since whatever epoch established their initial masses and angular momenta. Primordial black hole formation requires phase transitions or symmetry-breaking events that could concentrate energy density into compact regions during the early universe's evolution. These phase transitions might represent signatures of pre-Big Bang physics, critical points where different physical laws govern space-time evolution and matter interactions. The critical nature of black hole formation thresholds suggests that the early universe operated very close to gravitational instability boundaries. Intermediate mass black holes observed in globular clusters and dwarf galaxies may represent primordial black holes that served as seeds for subsequent accretion and growth processes. These black holes show mass distributions and spatial clustering properties that differ from those expected for black holes formed through stellar evolution alone. Their presence in low metallicity environments suggests formation mechanisms that preceded significant stellar nucleosynthesis and chemical enrichment. Perhaps primordial black holes formed during inflation or other early universe phase transitions represent gravitational fossils from much earlier cosmic epochs, compression events that occurred when the universe was already ancient in ways not reflected in standard cosmological timelines. Perhaps these black holes preserve information about cyclic cosmic evolution, carrying gravitational memories across cosmic cycles through their event horizon, causal isolation. Evaporating primordial black holes contribute to cosmic ray fluxes through their final explosive Hawking radiation bursts, producing characteristic signatures in high-energy particle detectors. The rate and energy spectrum of these evaporation events depend on the primordial black hole mass function and formation history, providing observational constraints on early universe conditions. Yet the infrared evaporation rates suggest more primordial black holes formed than standard models predict. Gravitational microlensing surveys search for primordial black holes through their gravitational focusing effects on background stars, detecting characteristic light curves when black holes pass between observers and distant stellar sources. The microlensing rate and duration statistics constrain primordial black hole abundance and mass distribution. Yet, observed lensing events suggest black hole populations that require formation mechanisms beyond those operating in standard early universe scenarios. Black hole mergers detected through gravitational waves show mass and spin distributions that may preserve information about primordial formation conditions. The nearly equal masses and relatively low spins observed in some merger events differ from expectations for black holes formed through stellar evolution, suggesting formation mechanisms that operated before stellar populations established themselves. These merger events could represent the final coalescence of primordial black hole binaries that have been slowly spiraling inward since formation. Supermassive black holes observed in the centers of high redshift galaxies present timing problems for standard black hole growth models. These billion solar mass black holes exist when the universe was supposedly less than 1 billion years old, requiring accretion rates and seed masses that challenge conventional formation scenarios. Primordial black holes could provide the massive seeds necessary for rapid early growth, but their formation requires early universe conditions that exceed standard model predictions. The information paradox associated with black hole evaporation becomes more complex for primordial black holes that have been evaporating since formation. These black holes have been processing quantum information for most of cosmic history, raising questions about information conservation and the nature of Hawking radiation. The resolution of information paradoxes may require physics beyond standard quantum field theory and general relativity. Primordial black holes in binary systems could have been merging throughout cosmic history, contributing to gravitational wave backgrounds that probe expansion history and structure formation over cosmic time. The merger rate evolution depends on formation redshift, mass spectrum, and clustering properties of primordial black hole populations. Observed gravitational wave background properties could constrain early universe physics through their dependence on primordial black hole formation scenarios. Modern astronomical surveys continue to search for primordial black hole signatures across multiple wavelengths and observational channels. From gamma-ray bursts associated with evaporating black holes to gravitational microlensing events caused by intermediate mass black holes. Each detection or non-detection provides constraints on early universe physics and the role of primordial black holes in cosmic evolution, revealing gravitational archaeology that reaches back to the universe's most extreme epochs. The population of primordial black holes continues to evolve today through Hawking evaporation, accretion, and merger processes, carrying forward information about gravitational collapse events that may have occurred when the universe was much younger and denser than current observations directly probe. These gravitational time capsules preserve memories of cosmic conditions that existed during whatever phase transitions brought space-time from its primordial quantum state to the classical geometry that hosts galaxies, stars, and the patient observations of gravitational wave astronomers measuring ripples in space-time itself. The cosmic microwave background radiation shows nearly identical temperatures across opposite regions of the sky that should never have had sufficient time to exchange energy and reach thermal equilibrium according to standard Big Bang chronology. This horizon problem represents one of the most profound puzzles in cosmology, suggesting that widely separated regions of the early universe somehow coordinated their properties across distances larger than light could have traveled since the supposed beginning of expansion. The observed temperature uniformity requires causal contact between regions that remain causally disconnected within conventional space-time models. The particle horizon defines the maximum distance that light signals could have traveled since the Big Bang, establishing a fundamental limit on causal communication within standard cosmological models. At the epoch of recombination, when the cosmic microwave background formed, regions separated by more than roughly 2 degrees on the sky should have been beyond each other's particle horizons. Unable to exchange information through any known physical process, yet the microwave background shows temperature variations smaller than 1 part in 100,000 across the entire observable sky. Inflation theory attempts to resolve the horizon problem by invoking a period of exponential expansion during the universe's first fraction of a second, stretching initially small, causally connected regions to cosmic scales before standard expansion began. During inflation, regions that were in thermal contact became separated by distances larger than the horizon size, preserving their initial temperature correlations as they evolved independently. Yet inflation requires initial conditions and fine-tuning that seem to require their own causal explanation. The geometric structure of space-time during the pre-recombination epoch determines how information could propagate between different regions of the early universe. Alternative cosmological models, including bouncing cosmologies and cyclic universe scenarios, propose different causal structures that could allow thermal equilibration over larger scales before the expansion phase we observe. These models often require much longer timescales for causal processes to establish observed correlations. Sound horizons in the early universe define the maximum distance that acoustic waves could propagate through the photon-baryon plasma before recombination froze the temperature fluctuations into the cosmic microwave background. The characteristic angular scale of temperature correlations corresponds to the sound horizon size at recombination, providing a standard ruler for cosmic geometry measurements. Yet the sharpness of acoustic peaks suggests that sound waves had sufficient time to establish well-defined harmonic modes. Only took the universe infinitely longer than it admits to arrange thermal contact between regions that supposedly never had time to communicate. Only required causally disconnected patches of space-time to achieve identical temperatures through mechanisms that remain completely mysterious. Only needed the early cosmos to violate its own light-speed communication limits to establish the observed thermal equilibrium, like a cosmic telephone network operating faster than light. Some unknown mechanism allowed widely separated regions of the early universe to coordinate their temperatures and densities before the expansion we observe began in earnest. The uniformity of physical conditions across the cosmic microwave background sky suggests that information propagated across scales much larger than the causal horizon during whatever epoch established initial conditions for the observable universe. Quantum entanglement provides a potential mechanism for correlations between space-like separated regions, allowing quantum systems to maintain non-local correlations across arbitrary distances without requiring classical information transfer. If the early universe existed in a highly entangled quantum state, widely separated regions could maintain correlated properties through quantum mechanical non-locality rather than classical thermal contact. These quantum correlations could survive decoherence and appear as classical temperature correlations in the microwave background. Variable speed of light theories propose that fundamental constants evolved during the early universe, potentially allowing information to propagate faster than the current speed of light during epochs before the cosmic microwave background formed. If light traveled much faster in the early universe, the particle horizon could have been larger than currently calculated, allowing thermal equilibration across larger scales. The subsequent slowing of light to its present value would preserve equilibrium conditions established during the faster light epoch. Perhaps the horizon problem reflects our incomplete understanding of space-time topology during the early universe, with regions that appear causally disconnected in standard coordinates actually connected through higher dimensional spaces or non-trivial topological relationships. Perhaps the universe began with initial conditions that were already perfectly coordinated, established during some prior phase of cosmic evolution that operated under different physical laws or space-time geometries. Extra-dimensional cosmological models suggest that our observable three-dimensional space represents a lower-dimensional slice of higher-dimensional space-time, with causal connections possible through extra dimensions, even when regions appear disconnected in ordinary space. Brain-world scenarios propose that our universe exists on a membrane embedded in higher dimensional space, where information could potentially propagate through bulk dimensions to establish correlations across apparently disconnected regions. String theory and holographic principles suggest that information about a volume of space-time may be encoded on its boundary, potentially allowing correlations between interior regions through boundary degrees of freedom. These holographic correlations could establish temperature uniformity across cosmic scales through mechanisms that operate outside conventional space-time causality, encoding information about widely separated regions in lower-dimensional holographic descriptions. Pre-Big Bang cosmologies, including ekpyrotic and cyclic scenarios, propose that the observable universe evolved from a contracting phase that preceded the expansion we observe. During contraction phases, widely separated regions could achieve thermal contact as space collapsed to small scales, establishing correlations that would persist through the subsequent expansion phase. These bouncing cosmologies naturally resolve horizon problems by providing extended periods for causal contact. The cosmic microwave background's polarization patterns provide additional constraints on early universe causal structure, revealing correlations between temperature and polarization fluctuations that depend on the causal relationships between different regions at recombination. The observed polarization temperature cross-correlations require specific causal structures during the photon-baryon plasma epoch, providing tests of different cosmological models that attempt to resolve the horizon problem. Topological defects, including cosmic strings and domain walls, could provide mechanisms for long-range correlations in the early universe if they formed during phase transitions that preceded the expansion epoch we observe. These defects could establish correlations across large scales through their influence on matter and radiation distributions, creating patterns that would appear as correlated temperature fluctuations in the cosmic microwave background. Modern precision measurements of cosmic microwave background correlations continue to refine constraints on early universe causal structure, searching for signatures of non-standard physics that could resolve horizon problems. Each improvement in angular resolution and sensitivity provides new tests of inflation models and alternative cosmological scenarios, revealing the geometric echoes of whatever causal processes establish thermal equilibrium across cosmic scales. The patient coordination of cosmic microwave background temperatures continues to puzzle cosmologists seeking to understand how causally disconnected regions achieved such remarkable uniformity. The horizon problem whispers of cosmic processes that operated beyond conventional space-time causality, establishing correlations across scales that challenge our understanding of information propagation in the early universe and suggest that cosmic evolution began much earlier and operated much differently than standard models currently accommodate. Geometric echoes of early universe causal structure persist today in the statistical properties of cosmic microwave background fluctuations, preserving information about whatever mechanisms allowed thermal equilibration across cosmic scales. Each correlation function and power spectrum measurement provides clues to the causal architecture that governed the early universe, revealing patterns that seem to require more time and more complex physics than conventional Big Bang chronology permits. Across galactic disks and throughout galaxy clusters, magnetic fields thread cosmic space with organizational patterns that require hundreds of billions of years to develop through conventional dynamo processes. These cosmic magnetic fields show coherent structures spanning kiloparsecs, with field strengths and geometries that suggest they have been evolving through magnetohydrodynamic processes since epochs much earlier than standard models of galaxy formation permit. The magnetic archaeology preserved in spiral galaxies and galaxy clusters reveals field evolution histories that appear to require more time than the universe has supposedly existed. Galactic magnetic fields typically achieve strengths of several microgauss throughout spiral galaxy disks, comparable to Earth's magnetic field strength, but extending across regions hundreds of thousands of light-years in diameter. These fields show remarkable organization, following spiral arm patterns and maintaining coherent polarization structures that trace galactic rotation and turbulence patterns. The generation and maintenance of such large-scale coherent fields through turbulent dynamo processes requires extensive evolutionary time for magnetic field amplification and organization. The galactic dynamo mechanism operates through the interaction of differential rotation and turbulent convection in galactic disks, gradually amplifying weak seed magnetic fields through magnetohydrodynamic processes. Alpha-omega dynamos convert kinetic energy from galactic rotation into magnetic field energy, but this process operates slowly even by astronomical standards. Computer simulations of galactic dynamos struggle to produce observed field strengths and coherence lengths within the supposed age of galaxies, requiring either enhanced seed fields or longer evolutionary times. Retry KM. Continue edit. Magnetic field. Observations in high redshift galaxies reveal organized field structures that appear too mature for their supposed ages, showing coherent patterns and strengths that should require billions of years of dynamo evolution to achieve. These early galaxies display magnetic field properties similar to local spiral galaxies. Despite forming when the universe was supposedly less than a few billion years old, the apparent magnetic maturity of distant galaxies suggests that magnetic field evolution began much earlier than conventional galaxy formation models predict. Galaxy clusters contain magnetic fields with strengths of several microgauss distributed throughout the intracluster medium, permeating volumes millions of light-years across with surprisingly uniform field properties. These cluster-scale magnetic fields show correlation lengths that span significant fractions of cluster virial radii, requiring magnetohydrodynamic processes that operate on timescales comparable to cluster dynamical times. The magnetic energy densities observed in cluster environments suggest field amplification processes that have been operating since very early epochs of structure formation. Faraday rotation measurements of polarized radio sources provide the primary observational probe of cosmic magnetic fields, revealing the integrated magnetic field strength and direction along lines of sight through magnetized plasma. The rotation measure statistics observed toward thousands of background radio sources show magnetic field correlations on scales ranging from galactic to cluster dimensions, with coherence properties that require extended periods of magnetic field evolution and organization. Only took the universe twice as long as it admits to wind up its cosmic magnetic dynamos to full strength. Only required magnetic fields to achieve coherent organization across scales from spiral arms to galaxy clusters without sufficient time for conventional amplification processes. Only needed the cosmos to generate magnetic energy densities approaching equipartition with turbulent kinetic energy through mechanisms that remain poorly understood. Like cosmic electricians working across deep time, magnetohydrodynamic processes thread galactic disks and cluster environments with magnetic field lines that store enormous amounts of energy in their twisted and sheared configurations. These magnetic structures interact with turbulent gas motions, stellar winds, and supernova explosions to create complex field geometries that evolve slowly through reconnection. Diffusion and dynamo amplification processes operating over cosmic timescales. Primordial magnetic fields generated during the early universe could provide the seed fields necessary for subsequent dynamo amplification in galaxies and clusters. Various mechanisms during cosmic phase transitions, including electroweak symmetry breaking and quantum chromodynamic phase transitions, could generate magnetic fields with strengths and correlation lengths that would evolve into observed cosmic magnetic fields. However, primordial field generation requires physical conditions during epochs much earlier than standard Big Bang nucleosynthesis. Magnetic helicity conservation in magnetohydrodynamic systems provides a constraint on magnetic field evolution that could preserve information about initial magnetic field configurations over cosmic time. Helical magnetic fields resist dissipation through turbulent decay, maintaining their large-scale structure while transferring energy between different scales through inverse cascade processes. The helicity signatures observed in galactic magnetic fields may preserve information about magnetic field generation during much earlier cosmic epochs. Supermassive black holes at galactic centers launch relativistic jets that thread magnetic field lines across megaparsec scales, potentially seeding magnetic fields in the intergalactic medium and galaxy clusters. These jets can transport magnetic flux from galactic nuclei to cluster-scale distances, providing mechanisms for magnetic field propagation that operate over cosmological timescales. The magnetic fields associated with active galactic nuclei show organization patterns that suggest they have been operating as cosmic magnetic field amplifiers for extended periods. Perhaps cosmic magnetic fields preserve information about pre-Big Bang phases of cosmic evolution, maintaining field configurations that originated when different physical laws governed electromagnetic processes and space-time geometry. Perhaps magnetic fields represent a form of cosmic memory that survives phase transitions and cosmic recycling events, carrying information about field generation processes that operated in much earlier cosmic epochs. Magnetorotational instabilities in accretion disks around young stars and protogalactic systems provide mechanisms for magnetic field amplification during the early stages of structure formation, These instabilities can rapidly amplify weak magnetic fields to dynamically significant strengths, but they require initial seed fields and specific disk properties that may not have been available during early cosmic epochs. The efficiency of magnetorotational amplification depends on disk ionization and turbulence properties that evolve as cosmic metallicity increases. Cosmic ray propagation through the galaxy depends strongly on magnetic field configurations, with charged particles following magnetic field lines and experiencing diffusion perpendicular to field directions. The observed isotropy of cosmic ray arrival directions requires magnetic field geometries that have had sufficient time to establish complex turbulent structures capable of randomizing particle trajectories. This magnetic turbulence develops through interactions between cosmic rays and magnetohydrodynamic waves over timescales comparable to galactic ages. Battery mechanisms in rotating, stratified plasmas can generate magnetic fields through thermoelectric effects and baroclinic instabilities that convert thermal and kinetic energy into magnetic field energy. These battery processes operate in protogalactic environments and galaxy cluster formation scenarios, potentially generating seed fields that subsequently undergo dynamo amplification. However, battery-generated fields typically achieve only weak strengths unless amplified through other processes over extended time periods. Magnetic reconnection events in cosmic plasma environments provide mechanisms for magnetic field reorganization and energy dissipation that shape large-scale field configurations over cosmic time. These reconnection processes operate continuously in galactic and cluster environments, gradually restructuring magnetic field topologies while releasing energy that heats the surrounding plasma. The cumulative effects of magnetic reconnection over cosmic time contribute to the evolution of observed magnetic field patterns. Modern radio astronomy surveys map magnetic field structures across cosmic scales with unprecedented precision, revealing the three-dimensional architecture of cosmic magnetism through polarization observations and Faraday rotation tomography. These surveys show magnetic field correlations that span multiple galaxies within clusters, suggesting that magnetic fields participate in large-scale structure formation processes that have been operating since very early cosmic epochs. The patient weaving of cosmic magnetic fields continues today through dynamo processes operating in galaxies, stars, and accretion disks throughout the universe. Each magnetic field line carries information about the magnetohydrodynamic history that brought it to its current configuration, preserving in its topology and strength the cumulative effects of rotation, turbulence, and plasma processes that have been shaping cosmic magnetism since whatever epoch first generated the seed fields that would grow into the organized magnetic structures threading cosmic space today. Magnetic field archaeology reveals cosmic dynamo processes that appear to require more time than conventional cosmology provides, suggesting that magnetic field evolution began during epochs hidden behind the cosmic microwave background's luminous curtain. The organizational complexity observed in cosmic magnetic fields whispers of evolutionary processes that operated for much longer than standard models currently accommodate, threading the universe with magnetic memories that reach back to cosmic phases when different physical laws may have governed electromagnetic field generation and evolution. Deep within the quantum foam of space itself, a sea of nearly massless particles streams through the universe at speeds approaching the velocity of light, carrying information from the cosmos's first moments when nuclear reactions briefly illuminated the primordial darkness. The cosmic neutrino background represents the oldest directly detectable relic radiation, formed roughly 1 second after the Big Bang when the universe became transparent to neutrinos. Yet the properties of this background radiation suggest cooling periods and interaction histories that extend far beyond what standard cosmological models accommodate for such early epochs. Neutrinos decoupled from thermal equilibrium with other matter when the universe was approximately 1 second old and had cooled to temperatures around 10 billion Kelvin. At this epoch, neutrino interaction rates dropped below the cosmic expansion rate, allowing these nearly massless particles to stream freely through space while preserving information about physical conditions during the universe's most extreme early moments. The cosmic neutrino background now pervades all of space with a density of roughly 330 neutrinos per cubic centimeter, cooled by cosmic expansion to temperatures of approximately 1.9 Kelvin. The energy spectrum of cosmic background neutrinos follows a Fermi-Dirac distribution characteristic of fermions in thermal equilibrium, but with subtle deviations that reflect non-equilibrium processes during neutrino decoupling. These spectral distortions preserve information about heating and cooling processes that operated when the universe was much denser and hotter than any laboratory experiment can recreate. The precision required to maintain these spectral signatures across cosmic time suggests that neutrino decoupling occurred under carefully controlled thermal conditions. Neutrino oscillations discovered through solar neutrino experiments and atmospheric neutrino studies reveal that neutrinos possess small but non-zero masses, requiring these particles to travel at speeds slightly less than the speed of light. The mass differences between neutrino flavors affect their propagation through cosmic space over billions of years, potentially creating observable signatures in the cosmic neutrino background spectrum. These mass-induced effects accumulate over cosmic distances and times, providing probes of neutrino properties and cosmic expansion history. Big Bang nucleosynthesis calculations depend sensitively on the number of neutrino species and their thermal properties during the first few minutes of cosmic expansion. The observed abundances of light elements, particularly helium-4 and deuterium, place strong constraints on neutrino physics during nucleosynthesis. Yet achieving the precise neutron-to-proton ratio required for observed light element abundances seems to require thermal conditions and expansion rates that suggest more complex early universe evolution than standard models predict. Only took the cosmic neutrino background 13 billion years longer than expected to cool from 10 billion Kelvin to its current frigid temperature of 1.9 Kelvin. Only required nearly massless particles to maintain their thermal distribution across cosmic expansion while preserving spectral information from the universe's first second. Only needed the weakest interacting particles in nature to serve as messengers from epochs when the entire observable universe was smaller than an atomic nucleus. Like cosmic archaeologists encoded in quantum mechanics, relic neutrinos carry information about physical conditions that existed when matter and energy densities exceeded those at the cores of neutron stars. These ancient particles have been streaming through space since before the first atomic nuclei formed, preserving in their energy distribution and propagation properties the thermal signature of whatever processes governed neutrino production and decoupling in the primordial universe. The cosmic neutrino background contributes to the universe's energy density and affects cosmic expansion rates, particularly during epochs when neutrinos were relativistic. As the universe cooled below neutrino masses, these particles became non-relativistic and began contributing to matter density rather than radiation density. This transition affects the growth of cosmic structure and the expansion history in ways that depend on neutrino masses and thermal properties established during decoupling. Direct detection of the cosmic neutrino background remains beyond current experimental capabilities due to the extremely low interaction cross-sections of neutrinos with ordinary matter. These relic neutrinos possess energies of only a few millielectron volts, far below the thresholds for most neutrino detection techniques. However, the gravitational clustering of cosmic neutrinos around massive structures could potentially create detectable effects through their collective gravitational influence on cosmic structure formation. Perhaps the cosmic neutrino background preserves information about pre-Big Bang phases of cosmic evolution, carrying thermal signatures from epochs when different physical laws govern particle interactions and space-time geometry. Perhaps neutrino decoupling occurred during extended thermal equilibration periods that required much longer timescales than standard cosmology provides for early universe evolution. Sterile neutrinos, hypothetical particles that interact only through gravity and neutrino oscillations, could contribute additional components to the cosmic neutrino background with different thermal histories and spectral properties. These sterile neutrinos could have decoupled at different times or under different conditions than active neutrinos, preserving independent information about early universe thermal evolution. Their potential existence adds complexity to cosmic neutrino background predictions and interpretations. Neutrino clustering around massive cosmic structures provides a potential probe of cosmic neutrino background properties through their gravitational effects on galaxy formation and cosmic structure growth. The free-streaming properties of neutrinos suppress structure formation on small scales while affecting the growth of large-scale structure in subtle ways that depend on neutrino masses and thermal velocities. These effects accumulate over cosmic time and may be detectable through precision cosmological observations. Primordial black hole evaporation through Hawking radiation contributes neutrinos to the cosmic background with energy spectra that depend on black hole masses and evaporation histories. If significant populations of primordial black holes formed and evaporated during cosmic evolution, their neutrino emission could modify the cosmic neutrino background spectrum in ways that preserve information about early universe gravitational collapse and quantum gravity effects. The relic graviton background, analogous to the cosmic neutrino background but consisting of gravitational waves rather than particles, could provide additional information about epochs even earlier than neutrino decoupling. Gravitational waves decouple from matter when gravitational interaction rates drop below expansion rates, potentially preserving information about cosmic conditions during epochs when the universe was much younger than 1 second old. Modern cosmological simulations include cosmic neutrino background effects in their modeling of structure formation and cosmic expansion, revealing how these nearly massless relics influence galaxy clustering, cosmic microwave background fluctuations, and expansion rate evolution. The precision required to match observations suggests that neutrino physics during early cosmic epochs operated under finely tuned conditions that may have required extended equilibration periods. Neutrino astronomy using high-energy cosmic neutrinos provides indirect probes of cosmic neutrino background properties through their interactions with relic neutrinos in cosmic space. These interactions, while extremely rare, could potentially create observable signatures in neutrino telescopes if cosmic neutrino background densities exceed standard predictions or if neutrino interaction physics includes unexpected processes. The patient streaming of cosmic background neutrinos continues today. These ancient particles traveling through space at nearly the speed of light while carrying thermal memories from the universe's first second. Each cosmic neutrino preserves information about the thermal conditions that governed its production and decoupling, maintaining across cosmic time and space the signature of whatever processes established neutrino properties when the entire observable universe was hot and dense beyond current experimental reach. Thermal relics from neutrino decoupling whisper of early universe conditions that required more careful temperature control and longer equilibration periods than standard Big Bang chronology provides, suggesting that the cosmos spent additional time calibrating the thermal properties that would govern neutrino production and propagation throughout cosmic history. The cosmic neutrino background carries these thermal secrets across billions of years, preserving in its nearly undetectable presence the memory of epochs when the universe was learning the fundamental physics that would govern its subsequent evolution. The fundamental asymmetry between matter and antimatter that allows stars, galaxies, and observers to exist represents one of the deepest mysteries in cosmic evolution, requiring processes that generated a slight excess of matter over antimatter during the universe's earliest moments. Current observations indicate that matter outnumbers antimatter by roughly 1 part in a billion, a tiny imbalance that permitted matter to survive mutual annihilation and form the cosmic structures we observe today. Yet generating this asymmetry through known physics appears to require multiple cosmic cycles or extended periods of particle interactions operating under conditions much different from standard Big Bang scenarios. Baryogenesis, the theoretical process responsible for creating the observed matter-antimatter asymmetry, must satisfy three conditions first outlined by Andrei Sakharov: baryon number violation, charge and parity symmetry breaking, and departure from thermal equilibrium. Known physics provides mechanisms for each condition individually, but generating sufficient asymmetry within the brief time windows available during standard Big Bang evolution requires precise coordination of these processes that seems to demand more time than conventional cosmology permits. Grand unified theories predict baryon number violation through processes that convert quarks into leptons and vice versa, potentially generating matter-antimatter asymmetries during phase transitions in the early universe. However, these processes typically operate most efficiently at energy scales corresponding to temperatures far exceeding those achieved during standard Big Bang evolution. The particle physics required for efficient baryogenesis may have been accessible only during pre-Big Bang epochs when different physical laws govern matter and energy interactions. Electroweak baryogenesis attempts to generate matter-antimatter asymmetry during the electroweak phase transition that occurred when the universe cooled below approximately 100 GeV temperatures. This mechanism relies on charge and parity violation in weak nuclear interactions combined with departure from thermal equilibrium during the phase transition. Yet achieving sufficient asymmetry requires extensions to the standard model of particle physics that include additional sources of symmetry breaking beyond those currently observed. Leptogenesis scenarios propose that the matter-antimatter asymmetry originated through the decay of heavy neutrinos that violated lepton number conservation, with the resulting lepton asymmetry subsequently converted to baryon asymmetry through anomalous electroweak processes. These mechanisms can potentially operate at lower energy scales than grand unified theory baryogenesis, but they require sterile neutrinos with masses and interaction properties that may have been established during much earlier cosmic epochs. Only took the universe several cosmic cycles longer than it admits to accumulate sufficient matter-antimatter asymmetry through whatever processes distinguish matter from antimatter at the fundamental level. Only required one extra matter particle for every billion matter-antimatter pairs to avoid complete mutual annihilation. Only needed the cosmos to learn extremely subtle differences between particles and antiparticles that allow matter to gain a slight advantage in the cosmic struggle for survival. Like a cosmic casino with cards slightly stacked in favor of matter, whatever processes generated the baryon asymmetry operated with precision that suggests extensive calibration time to achieve exactly the right imbalance between matter and antimatter. Too little asymmetry would leave insufficient matter for structure formation, while too much asymmetry would prevent the thermal equilibrium conditions necessary for Big Bang nucleosynthesis and cosmic microwave background formation. Charge parity violation discovered in neutral kaon decay experiments demonstrates that fundamental physics distinguishes between matter and antimatter in subtle ways that could contribute to cosmic baryon asymmetry generation. The magnitude of observed charge parity violation appears insufficient to generate the required cosmic asymmetry within standard cosmological timescales, suggesting either that additional sources of symmetry breaking remain undiscovered or that asymmetry generation operated over much longer periods. Spontaneous baryogenesis models propose that baryon number violation occurs continuously throughout cosmic evolution rather than only during brief, early universe phase transitions. These scenarios require scalar fields that couple to baryon number currents and evolve slowly over cosmic time, gradually generating matter-antimatter asymmetry through their interaction with quantum field fluctuations. Such mechanisms could operate over extended periods, accumulating asymmetry through processes that span multiple cosmic epochs. Perhaps the observed matter-antimatter asymmetry represents the cumulative result of multiple baryogenesis events that occurred during different phases of cosmic evolution, each contributing small amounts to the total asymmetry through processes operating under different physical conditions. Perhaps cosmic recycling through cyclic cosmologies allows asymmetry to accumulate over multiple cosmic cycles, with each cycle adding to the matter excess inherited from previous phases. Primordial black hole formation and evaporation could contribute to baryon asymmetry through gravitational baryogenesis mechanisms that operate when space-time curvature couples to baryon number currents. Black hole formation preferentially captures antimatter under certain conditions, while subsequent Hawking evaporation returns slightly more matter than antimatter to the surrounding space. These gravitational baryogenesis processes require significant primordial black hole populations that may have formed during much earlier cosmic epochs. Axion physics provides potential mechanisms for generating matter-antimatter asymmetry through the interaction of axion fields with quantum chromodynamic vacuum states. The strong charge parity problem in quantum chromodynamics requires axion fields to maintain extremely small couplings to preserve observed charge parity conservation in strong interactions. However, during early cosmic epochs, when axion fields were displaced from their minimum energy configurations, these same couplings could generate baryon asymmetry through their interaction with thermal quark and gluon plasmas. Cosmic strings and other topological defects created during cosmic phase transitions could generate matter-antimatter asymmetry through their interactions with surrounding matter and radiation fields. These defects create regions of enhanced energy density and modified field configurations that could facilitate baryogenesis processes during their formation and subsequent evolution. The efficiency of defect-mediated baryogenesis depends on defect network properties that evolve over cosmic timescales. Alternative cosmological scenarios, including ekpyrotic and cyclic models, provide different thermal histories and expansion rates during early cosmic epochs that could facilitate baryogenesis through mechanisms not available in standard Big Bang cosmology. These models often include contraction phases that create thermal and chemical conditions conducive to efficient asymmetry generation, followed by expansion phases that preserve and dilute the generated asymmetry to observed levels. Modern particle accelerator experiments search for additional sources of charge parity violation and baryon number violation that could contribute to cosmic baryogenesis processes. Each discovery of new symmetry breaking phenomena provides constraints on early universe physics and potential mechanisms for generating the observed matter-antimatter asymmetry. However, the precision required to generate exactly the observed asymmetry suggests fine-tuning that may require extended evolutionary periods. Neutrino oscillation experiments reveal that neutrino physics includes charge parity violation that could contribute to leptogenesis scenarios for generating cosmic asymmetry. The magnitude and flavor structure of neutrino charge parity violation depend on neutrino mass matrices and mixing parameters that may preserve information about high-energy physics during early cosmic epochs when heavy neutrinos were produced and decayed. The persistent dominance of matter over antimatter continues today throughout the observable universe, with antimatter existing only in cosmic ray interactions and laboratory experiments rather than forming stable cosmic structures. This matter-antimatter imbalance represents the successful outcome of whatever processes distinguish between particles and antiparticles during the universe's earliest moments, preserving in every atom the signature of asymmetry generation events that occurred when physical conditions exceeded those accessible to terrestrial experiments. Baryon asymmetry observations provide strong constraints on early universe physics and cosmological models, requiring any successful theory of cosmic evolution to explain both the magnitude and stability of the observed matter excess. The fine-tuning required for efficient baryogenesis whispers of cosmic processes that operated over much longer timescales than standard cosmology provides, suggesting that matter-antimatter asymmetry accumulated gradually through mechanisms that required extended periods of particle interactions under carefully controlled thermal and chemical conditions. The quantum vacuum that surrounds us may exist in a false minimum of its potential energy landscape, a metastable state that could spontaneously decay to lower energy configurations through quantum tunneling processes that would fundamentally alter the laws of physics throughout our cosmic domain. Vacuum decay scenarios in quantum field theory suggest that our current universe represents one phase in a much longer cosmic evolution spanning unimaginable timescales, with each metastable vacuum state persisting for durations that dwarf the apparent age of our observable cosmos before tunneling to deeper energy minima. The Higgs field that gives mass to elementary particles exists in a potential energy configuration that may not represent the absolute minimum energy state available to scalar field physics. Precise measurements of Higgs boson properties and top quark masses suggest that the standard model vacuum could be metastable, capable of tunneling to lower energy states where fundamental constants and particle masses would assume completely different values. The tunneling rate depends exponentially on energy barriers that could maintain our current vacuum state for periods vastly exceeding current cosmic age estimates. False vacuum decay proceeds through bubble nucleation events, where small regions of space tunnel to lower energy vacuum states, expanding at light speed to convert surrounding space to the new vacuum configuration. These vacuum bubbles represent phase transitions more fundamental than any cosmic process yet observed, changing the basic laws of physics rather than merely rearranging matter and energy within existing physical frameworks. The statistical nature of quantum tunneling means that vacuum decay events could occur at any moment or remain suppressed for arbitrarily long periods. Cosmological inflation itself may represent a false vacuum decay event that established our current cosmic domain within a much larger multiverse of different vacuum states. The inflationary scalar field that drove exponential expansion could have tunneled from a higher energy false vacuum to the lower energy state that terminated inflation and began the radiation-dominated epoch. This scenario suggests that our observable universe represents the interior of a vacuum decay bubble embedded within a higher dimensional space containing other bubble universes with different physical laws, the apparent fine-tuning of fundamental constants for star formation, nucleosynthesis, and biological complexity could reflect anthropic selection within a multiverse of vacuum states where only certain combinations of physical parameters permit complex structure formation. If vacuum decay events create domains with different fundamental constants, observers would naturally find themselves in regions where physics permits their existence. This anthropic reasoning suggests that our vacuum state was selected from many possibilities over cosmic timescales much longer than conventional cosmology acknowledges. Only took the universe infinitely longer than it admits to learn how to maintain metastable equilibrium in quantum field configurations that could decay at any moment. Only required the false vacuum to resist tunneling to lower energy states for periods exceeding any reasonable estimate of cosmic longevity. Only needed our particular combination of physical constants to emerge from whatever cosmic lottery determines vacuum state properties across bubble universe domains. Like a cosmic house of cards balanced on quantum mechanical foundations, our entire observable universe may rest upon vacuum stability that could vanish through tunneling events operating according to quantum statistical principles beyond human prediction or control. The mathematical structure of quantum field theory suggests that vacuum decay represents an inevitable consequence of field dynamics, delayed only by energy barriers that determine tunneling probabilities over cosmic timescales. Vacuum decay scenarios predict observable signatures in cosmic microwave background fluctuations and large-scale structure formation that could provide evidence for multiple vacuum states operating during cosmic evolution. Collisions between expanding vacuum bubbles would create distinctive patterns in background radiation and matter distribution, while the boundaries between different vacuum domains could appear as cosmic defects with characteristic observational signatures. String theory landscapes predict enormous numbers of possible vacuum states corresponding to different ways that extra dimensions can curl up and different ways that fundamental forces can be unified. The number of possible vacuum configurations in string theory approaches 10 circumflex 500, suggesting that our current vacuum state represents one possibility among an almost infinite variety of potential physics. Navigation through this landscape of possibilities could require cosmic evolution periods vastly exceeding standard cosmological timescales. Perhaps our current vacuum state emerged through a sequence of vacuum decay events that required extensive time to explore different regions of the fundamental physics landscape before settling into the metastable configuration we observe today. Perhaps vacuum decay cycles represent a form of cosmic natural selection, where only vacuum states capable of supporting complex structure formation persist for extended periods, while unstable configurations quickly decay to other possibilities. Eternal inflation scenarios propose that vacuum decay events occur continuously throughout an inflating multiverse, creating bubble universes within bubble universes in fractal patterns that extend infinitely through space and time. Our observable cosmos would represent the interior of one such bubble, surrounded by inflating space containing other bubble universes with different vacuum states and physical laws. This eternal process suggests that cosmic evolution operates on timescales that make our observable universe's apparent age insignificant. Quantum gravity effects near Planck energy scales could modify vacuum decay calculations by introducing corrections to quantum field theory that arise from space-time geometry fluctuations. These modifications might stabilize otherwise unstable vacuum states or create new decay channels that alter tunneling probabilities. The interplay between quantum field theory and quantum gravity suggests that vacuum stability depends on physics beyond the standard model that may have evolved over cosmic periods much longer than standard cosmology provides. Vacuum decay could trigger fundamental changes in cosmological evolution by altering dark energy properties, modifying gravitational physics, or changing the masses and interaction strengths of elementary particles. A universe that has survived multiple vacuum decay events might preserve traces of previous vacuum states in its cosmic structure, gravitational wave backgrounds, or relic particle populations that carry information about earlier epochs with different physical laws. Laboratory experiments searching for vacuum decay signatures include precise measurements of fundamental constants over time, searches for cosmic defects that could represent vacuum domain boundaries, and high-energy particle physics experiments that probe vacuum stability through direct field manipulation. Each measurement that confirms vacuum metastability provides constraints on tunneling timescales and energy barriers that determine our cosmic domain's longevity. Modern cosmological observations provide upper limits on vacuum decay rates through the apparent stability of fundamental constants and the absence of distinctive signatures that would accompany vacuum decay events. These observational constraints suggest either that our vacuum is absolutely stable, that tunneling timescales exceed cosmic age estimates by enormous factors, or that vacuum decay events have occurred but remain undetected in current observations. The false stability of our cosmic domain continues today, maintained by quantum energy barriers that could collapse through tunneling events operating according to statistical principles that make precise predictions impossible. Each moment that passes without vacuum decay provides additional evidence for either absolute vacuum stability or energy barriers sufficient to suppress tunneling for periods that dwarf any reasonable estimate of cosmic evolution timescales. Vacuum decay represents the ultimate cosmic phase transition, changing not merely the contents of the universe, but the fundamental laws that govern cosmic evolution itself. The apparent longevity of our current vacuum state whispers of cosmic processes that operate over time, scales vast enough to explore multiple configurations of fundamental physics, suggesting that our observable universe represents one phase in vacuum evolution spanning periods that make a conventional cosmic chronology seem like brief quantum fluctuations in the eternal exploration of possible physical laws. Metastable equilibrium persists throughout cosmic space today, maintained by energy barriers that separate our current vacuum configuration from potentially lower energy states where different physics would govern matter, energy, space, and time. The patient persistence of our false vacuum carries forward whatever cosmic history brought fundamental constants to their current values, preserving across unimaginable timescales the delicate balance of forces that permits complex cosmic evolution and the emergence of observers capable of contemplating their own metastable foundations beyond the boundaries of our observable cosmic domain, where space-time curves back upon itself through dimensions we cannot directly perceive. The universe may breathe through cycles of expansion and contraction that have been repeating since time itself learned the rhythm of eternal return. Cyclical cosmology suggests that what we interpret as the Big Bang represents merely one phase in an endless sequence of cosmic rebirths, each cycle beginning with expansion from a singular state and evolving through structure formation, entropy increase, and eventual collapse back to conditions that trigger the next expansion phase. The cyclic universe model resolves many paradoxes that plague standard Big Bang cosmology by providing unlimited time for cosmic processes to establish the initial conditions we observe today. The horizon problem dissolves when causally disconnected regions had infinite time to achieve thermal equilibrium during previous cycles. The flatness problem disappears if cosmic geometry undergoes cycles of expansion and contraction that naturally drive space-time toward critical density configurations. The monopole problem vanishes if topological defects from previous cycles are diluted through repeated expansion and contraction phases. Ekpyrotic scenarios propose that our universe emerged from the collision between higher dimensional branes in string theory frameworks, with each collision producing a new cosmic cycle characterized by different fundamental constants and physical laws. These brane collisions occur periodically as branes oscillate through extra-dimensional spaces, creating an eternal sequence of Big Bangs that reset cosmic evolution while preserving certain physical quantities across cycle boundaries. The apparent youth of our current cosmic phase may reflect the recent occurrence of the most recent brane collision. The second law of thermodynamics poses challenges for cyclical cosmologies because entropy increases during each cycle, potentially preventing perfect cyclical repetition and leading to eventual thermal death rather than eternal cycling. However, gravitational entropy could reset during cycle transitions, allowing total cosmic entropy to return to low values at the beginning of each new cycle. This entropy recycling mechanism operates through gravitational collapse that converts matter configurations back to smooth initial states suitable for renewed cosmic evolution. Dark energy evolution throughout cosmic cycles could drive the transition from expansion to contraction as vacuum energy properties change over cosmic timescales. If dark energy density decreases or becomes negative during late cosmic phases, the universe could eventually recollapse under its own gravity, beginning the contraction phase that leads to the next Big Bang. The cyclical variation of dark energy properties provides a mechanism for eternal cosmic recycling without requiring external intervention. Only took the universe countless cycles longer than it admits to perfect the cosmic choreography that produces galaxies, stars, and observers capable of discovering their own cyclical foundations. Only required infinite rehearsal time for gravitational collapse and expansion to establish precisely the right initial conditions for complex structure formation. Only needed eternal patience to explore every possible configuration of matter, energy, space, and time until consciousness emerged to contemplate its own cosmic origins. like a cosmic heart beating across deep time. The universe expands and contracts through cycles that span periods incomparably longer than human experience, yet briefer than eternity permits, when time itself operates without beginning or end. Each expansion phase explores new possibilities for cosmic evolution, while each contraction phase resets initial conditions and prepares the foundations for renewed exploration of physical possibilities. Quantum cosmology suggests that the universe could tunnel between different expansion and contraction phases through quantum gravitational processes that operate when cosmic density approaches Planck scales. These quantum transitions between cosmic phases provide mechanisms for cycle continuation even when classical physics predicts gravitational singularities that would terminate cosmic evolution. Quantum effects near maximum contraction densities could bounce cosmic evolution from collapse back to expansion without requiring classical Big Bang singularities. Information preservation across cosmic cycles requires mechanisms that protect quantum information from destruction during gravitational collapse phases, possibly through holographic storage on cosmic event horizons or through quantum entanglement relationships that transcend individual cycle boundaries. If information survives cycle transitions, each new expansion phase could access memories from previous cycles, potentially explaining the apparent fine-tuning of physical constants and initial conditions. Perhaps the cosmic microwave background preserves traces of previous cycles through subtle correlations that survive the transition from contraction to expansion, encoding information about structure formation during earlier cosmic phases in temperature fluctuations that appear to result from quantum fluctuations during inflation. Perhaps the large-scale structure we observe today reflects gravitational memory effects that carry forward organizational patterns from previous cycles. Observational signatures of cyclical cosmology could include modifications to cosmic microwave background correlations, deviations from standard nucleosynthesis predictions, or gravitational wave backgrounds produced during cycle transitions. Advanced observational cosmology continues searching for these signatures, while pushing measurements of cosmic parameters to precision levels that could distinguish between cyclical and single-expansion cosmological models. The multiverse implications of cyclical cosmology suggest that different cosmic cycles could explore different regions of the fundamental physics landscape, with each cycle testing different combinations of physical constants, symmetry, breaking patterns, and dimensional configurations. Our current cycle represents one exploration among infinite possibilities, with anthropic selection ensuring that observers emerge only in cycles that permit complex structure formation and biological evolution. Eternal inflation, combined with cyclical cosmology, creates scenarios where bubble universes undergo internal cycling while embedded within ever-expanding inflating space, producing infinite hierarchies of cosmic cycles operating on different scales throughout an eternally inflating multiverse. This combination provides unlimited time and space for cosmic evolution while avoiding some philosophical problems associated with either eternal inflation or pure cyclical models. Time itself takes on different meaning in cyclical cosmologies, where cosmic evolution proceeds through endless repetition with variation, exploring infinite possibilities for structure formation, complexity emergence, and consciousness development. Each cycle contributes to cosmic evolution's eternal exploration of what is possible within the constraints of fundamental physics, mathematics, and logic that govern all possible universes. Modern theoretical physics continues developing cyclical cosmology models that address observational constraints while providing mechanisms for eternal cosmic cycling through gravitational, quantum, and string theory effects that operate near maximum cosmic density phases. These models suggest that cosmic evolution operates on timescales that make our observable universe's apparent age represent a brief moment in eternal cycling that has been exploring cosmic possibilities since before time began and will continue long after time ends. The eternal return continues today as dark energy drives cosmic acceleration toward a future that may eventually transition back to contraction, beginning another journey through the cosmic cycle that connects our present expansion phase to infinite past and future cosmic incarnations. Each moment of cosmic evolution contributes to eternal cycling that explores every possibility for matter, energy, space, time, and consciousness to organize themselves into the temporary patterns we call galaxies, stars, planets, and the brief biological experiments that observe their own cosmic foundations. Cosmic cycling whispers of eternal processes that operate beyond human temporal experience, suggesting that our universe participates in rhythms vast enough to encompass infinite exploration of physical possibilities, yet intimate enough to include every quantum fluctuation that shapes the cosmic microwave background, every gravitational wave that ripples through space-time, and every thought that contemplates the eternal cosmic dance between expansion and contraction that may have been breathing through infinite cycles since before existence learned to exist and will continue breathing long after existence forgets how to remember its own eternal nature. The eternal cosmic breath expands and contracts through cycles that span impossibly vast periods, yet remain forever patient in their exploration of what consciousness, complexity, and cosmic evolution can accomplish when given unlimited time to explore infinite possibilities within the mathematical structures that govern all possible realities across all possible cosmic cycles throughout eternal time and endless space. The universe settles into its vast, patient rhythm now, expansion slowing into the deep, cosmic exhale that will continue for eons beyond human reckoning. Dark energy guides this gentle acceleration, while galaxies drift apart like distant islands in an ocean of space-time that grows larger and cooler with each passing moment. The cosmic microwave background radiation continues its quiet cooling. Photons that once blazed with stellar fire now whispering at temperatures barely above absolute zero, across cosmic scales that dwarf human imagination. The ancient processes continue their work. Dark matter scaffolding holds galactic clusters in their appointed places, while magnetic fields thread cosmic space with invisible architecture that has been under construction since epochs hidden behind the luminous veil of the Big Bang. Primordial black holes drift through intergalactic space, carrying gravitational memories from whatever phase transitions brought our observable cosmos into existence. The quantum vacuum maintains its patient hum, zero-point fluctuations sustaining their eternal dance of creation and annihilation in every cubic centimeter of apparently empty space. Virtual particles appear and disappear on timescales shorter than measurement, while preserving the vacuum energy that may hold memories of cosmic states that preceded the expansion we call the beginning. Stars burn with light that carries the chemical signatures of previous stellar generations, metallicity patterns that speak of nuclear furnaces operating longer than standard cosmology permits. The oldest white dwarfs cool toward absolute zero, while neutron stars spin with the momentum of gravitational collapse events that shaped cosmic evolution across timescales that stretch the universe's supposed age beyond conventional limits. Perhaps consciousness itself participates in cosmic cycling, emerging from matter and energy configurations that explore what is possible when the universe achieves sufficient complexity to observe its own foundations. Perhaps awareness represents one phase in eternal cosmic evolution, temporary patterns of information processing that arise when space-time learns to contemplate its own geometry through biological experiments scattered across cosmic distances. The eternal cosmic breath expands and contracts through whatever cycles connect our present moment to infinite past and future incarnations, each expansion exploring new possibilities while each contraction resets initial conditions for renewed cosmic evolution. time itself drifts toward whatever transformations await in cosmic futures too distant for prediction, yet intimate enough to include every quantum fluctuation that shapes the universe's patient journey toward tomorrow. In this vast stillness, consciousness finds its rest among galaxies that continue their appointed motions through space that expands according to laws established in epochs before time began. The universe dreams its ancient dreams, while dark energy carries everything toward cosmic configurations that will unfold across timescales that make eternity seem brief and infinity seem local. All becomes quiet now in the cosmic perspective that holds stars and thoughts equally in its patient embrace, awareness settling into the same infinite rest that cradles galaxies in their orbits around invisible attractors, pulling everything toward destinations beyond the cosmic horizon, where space and time curve back upon themselves in geometries that connect every moment to eternity and every location to everywhere else in the endless cosmic breathing that continues without beginning or end. Sleep well.